So let's do this example here. Here's an example. Just put the question down here, and then I'm going to hopefully erase up here on top. So let's take an example with some matrices this time. Let's take the matrix 1, 0, 1, 2, comma, -1, 1, 2, 1. These are 2 by 2. And then 2, 1, 5, 7. We're going to take those three matrices and we're going to ask, is that Li or Ld? Is that Li or is that Ld? That's really the question. Okay, so we're going to back up to the top. I can't really win today with this. I'm just going to have to keep doing this the hard way. Okay. So, turns out to answer questions like this is really pretty straightforward. If you didn't really follow all the sort of the setup of this whole thing, now I'm going to show you how to do the problems. All you got to do, guys, is set up a matrix again. It's the running joke of linear algebra. The answer to every problem in this class is throw it in a matrix. Okay? So what are we going to do? We're going to make a matrix. And the way this matrix is going to look is just like it did for spanning sets. We're going to throw these vectors into the columns of this matrix. So this first vector is itself a matrix, but I have to sort of smear the four numbers of this matrix into the first column. So that's going to be 1, 0, 1, 2. Okay? And then the second matrix would go into the second column. And by the way, you notice I went from the top left to the top right to the bottom left to the bottom right when I put the first column in. That's kind of up to you, like what order you want to put the four numbers into this column. But whatever order you do it in for the first vector, for the first matrix, you must do it the same way for all of the others. So if I'm going from upper left, upper right to lower left to lower right, I got to do the same thing again for this second matrix, which is where I'm going to get -1, 1, 2, and 1. And similarly for the third matrix, 2, 1, 5, 7. Now, if I was asking if these matrices are a spanning set for the 2 by 2 matrices or something like that, I would augment this matrix with those hashtag number symbols. But we are now asking a different question. Are these vectors Li or Ld? So for that question, the big difference is that we're going to augment with zeros this time. Okay? But again, we're actually just going to do the EROs just like before. So I'm just going to take this matrix. Let me get it into row echelon form first. That's kind of the most important thing. And in fact, let me just skip to the row echelon form, and I'll let you guys check me if you want to, but I want to get to the punchline here. When you reduce this to row echelon form, actually what will happen, the first two rows you can see here and here, those are fine, those are the same. But it turns out that the other two rows just get wiped out. The other two rows will end up getting completely zeroed out. Don't worry so much about the fact that the rows are zeroing out. That's not what's important. What's important is really the pivots and the columns. That's what you want to pay attention to. So remember that your unknowns here, your unknowns in your linear system, those are the constants, the C1, the C2, the C3, which I've almost erased down here. The question is, do those constants have to be 0? Or can they possibly be other values? And what that really boils down to is whether there are any free variables or not. In this case, there is a free variable. The third column does not have a pivot, and that means that it is a free variable, and in particular, it's C3. That is a free variable. I will call it T. Okay? And then just as usual, going back to how we solve these linear systems, we can work backwards and solve for C2, which would be negative t coming from the second row of this matrix. So C2 plus C3 has to add up to 0. And then C1 should be equal to C2 minus 2C3, which is actually going to give me negative 3t, I believe. Let me just double check that I did that right. Yeah, negative 3t. Okay? So guys, because there's a free variable here, the constants, the C1, the C2, and the C3, they do not have to be all 0 in this linear combination. In other words, this is bad, right? This is not what we want. This basically tells me already that these vectors are LD, right? Remember how we were erasing vectors earlier, right? When we had unpivoted columns? Like if we threw away this vector right here, if we threw away that third vector, then we would have thrown away that column and that column, and now we don't have any free variables. Just the first two vectors alone would have been great. Spending $2,000 would have been fine, but we spent too much because we have another vector here, right? I'll go back and put it in. This vector got us an additional column, which turned out not to be a good thing because it gave us another constant, and this particular constant was free. In fact, we can even make this linear dependency that I was talking about. This is something you're going to need to be able to do if your vectors are LD. Namely, we can choose any value for t that we want, except don't choose 0. I don't want to make all my constants 0. I want to find an interesting linear combination. If t is equal to 1, then C1 becomes negative 3, C2 becomes negative 1, and C3 becomes 1. And what does that really mean? Well, that just means that we have an equation that we can make. Let me see if I can make the equation here. So in other words, negative 3 times the first vector, 1, 0, 1, 2, and then minus 1 times the second vector, which is negative 1, 1, 2, 1, and then plus the third vector, 2, 1, 5, 7. Well, that, if as long as I have not made a mistake, that should cancel out to the 0 vector. We can go through the 4 corners of the matrix and run the arithmetic across, and everything should be canceling out. We have managed to cancel out our vectors without just putting zeros in front of all of the vectors. And that's bad. That means these vectors are LD. We spent too much money and we should have gotten rid of something. So this is, again, this is what's called a linear dependency. It's a linear dependency. Okay? Hoping that that makes a little bit of sense. Let me do one more example. If you're good and you're following everything so far, you don't necessarily need to watch any further. But I want to do one more example just for those of you who like to see a lot of examples. I want to do one with some polynomials. Okay, so this is just going to be the same thing again, though. We're not really going to do anything different. It's just going to look different because of the fact that we have polynomials in this problem instead of matrices. So here's an example. I'm going to keep it pretty simple here. So here's the example. Is the set 3 plus x, comma 4 minus 2x, comma 6 plus 3x, Li or LD? Okay, so we'll just take those 3 polynomials right there and see whether they are Li or LD. Okay, let me come back up here. Give myself plenty of room for this. So guys, we're going to go straight to the augmented matrix, okay? So the solution to this, we're going to go really fast. We're going to go ahead and put the first vector into the first column. Now, when you're having polynomials, what we're really going to be doing is grabbing the coefficients of the different terms. So there's a 3 here, and then there's a 1 in front of the x. So I'm going to write that as 3. Actually, you know what? I'm going to put the x first. I can do it in whichever order I want. So I'm going to do the x on top and the 3 on the bottom. I can do that as long as I'm consistent with the second and third vectors the same way. So for the second vector, I have to put the x coefficient on top, then the constant. Third vector, same way, the 3 and then the 6. Okay, we're going to augment that now with 0, 0. Okay? And we're going to row reduce this. You can already tell, can't you, that we're going to get a free variable here. If I take -3 times the first row and add it to the second row, we're going to get something like this. You can already see, this is more or less where the pivots are going to end up. There is a free variable again on this problem. This is not good, right? This means we spent $3,000, but this third vector right here is causing the whole set to be LD, right? It's the unpivoted column that is the problem, because that's the one that gives you a variable. This is C3 that is going to be free. Okay, so again, we can now go back if we want, and we can solve for C1 and C2 and write out our linear dependency again, right? So for example, if C3 is equal to T, then if you just solve for C2, 10 times C2 minus 3T, let's just write this down, 10C2 minus 3T is 0. So C2 would be 3/10 of T. Okay, and then from the first row of the matrix, we could go back and solve for C1. And I actually did do that. I'm going to just go ahead and tell you what it is. It's -12/5 of T. So again, I'm just going to, I normally will just choose T equal to 1. There's really no reason that you have to choose any other numbers. And this just tells me then that -12/5 times my first vector, which is 3 plus x, and then plus 3/10 times my second vector, which is 4 minus 2x, and then plus my third vector, which is 6 plus 3x, all of that should equal 0. This is my linear dependency again. Okay, so we don't really like linear dependencies. We want to remove them because that means we've paid extra money and we're not getting any extra benefit from it, right? If I throw away the 6 plus 3x here, see, imagine I go back, and in fact, we will often do this. Imagine I go back and I ask you, is it a spanning, are those 3 polynomials a spanning set? So then I can actually double task here. I can actually get both my LI-LD question answered and my spanning question answered at the same time. And you can see that these 3 polynomials, they do span P1 of R. This is P1 of R, by the way, polynomials of degree 1 or less. The pivot does not go into the far right column. So that's a good thing, right? This is a spanning set. But the deal is that even if I didn't have the third column here, even if I got rid of that third vector that I paid $1,000 for, and I cross that off, and I cross that off there, I still don't have a pivot going into the far right column. These 2 pivots are still going to be in exactly those same spots, which means you still have a spanning set. But if you didn't have the third vector, you would not only have a spanning set, you would have saved some money, and your vectors would be Li instead of LD. You wouldn't have any linear dependencies to think about. So that is basically the story of linear dependence and linear independence. I hope it made some sense. I had fun sharing it with you, and I'm always going to be happy to answer questions and try to help put this stuff together. So we have spanning sets and we have linear independence. Those two concepts are really talked about side by side. And you can see that when you're solving problems about spanning sets and linear independence, you set them up in almost the same way. The only difference is what you're putting in the far right column. And you can often just double task and handle both of the questions at one time by doing the ERO process just one time. So that's kind of handy. All right, well, when I see you guys again, we will practice this some more. We will look at a big picture of what all of this means for our vector spaces. And I will certainly be happy to talk to you and take questions on it. Thanks for watching today. I hope you enjoyed it, and I look forward to talking to you guys all again real soon. Take care. Have a great rest of your day. Bye for now.